Hello students. So the question that we have here today says 12 wires each having equal resistance R are joined to form a cube as shown in the figure. Find the equivalent resistance between the diagonally opposite points A and F. So we'll try doing this question using two ways. This question is, though it looks a little complicated, the circuit as it is, once we understand how we approach this question, we'll see that the question can be solved very easily in just 2 or 3 steps, not more than that. And in fact, we have more than one ways of solving this question, so we'll look at all of them. So the first thing that we all need to understand is when the question has asked us to find out the equivalent resistance across 2 points in a given circuit. This basically means that we are essentially connecting our battery across those points. So here I have drawn the figure once again and we will work through the figure now. So first of all, in order to understand how the current flow takes place through the circuit, let us connect a battery. It gives us a visual idea as to how the current is moving through the circuit. So if I connect a battery between the points A and F, I see that the battery, if it provides a current I to the circuit, this current I, as it reaches the point A, it will tend to go through this whole circuit in order to reach the other point, the point F, which is connected to the negative terminal of the battery. We all know that current flows in a circuit from the positive terminal to of the battery towards the negative terminal, and in the process whatever resistors and whatever other components are there in the circuit, it flows through all of them. Here we have resistors which are connected in this particular form as is shown to you. So understand that our current I has to move from A to F, and if we try to identify the paths that are available with this current to move from the highest potential point A to the lowest potential point F, it will have various ways, it will have various paths through which the current can travel. We will be using the symmetry of this circuit to identify the way the current moves, the way it divides across different junctions, and that will help us find out, or it will help us distribute the current properly. Without using more variables, we will be able to distribute the current through the circuit, and then we should use the loop law, either the loop law or the other methods to find out the effective resistance. So as we try and identify that, let's look at a few things here in the circuit. See that as the current I reaches the junction A, it essentially has 3 paths to move from the point A. One is the path AB, this path, the other is the path AD, and the third one is the path AH. Yes. Now let's go a step ahead and see what happens when a current reaches from the point A to the point B. From point B, do you all see that the current has 2 paths to follow? From B, it can either go from B to C, or it can go from B to E. And if you look at it carefully, from C then the current will have a tendency to move down to F, because essentially current wants to move from A to F. All the current that reaches C will have a tendency to move towards the negative most potential point, which is the point F here in the circuit. Same thing will happen with the current that reaches from the point B to the point E. The current that reaches E will tend to move to the point F, the junction F. So essentially the current is getting divided across different junctions and it's moving from A to F. Now if you look at the symmetry of this figure, the current that moves from A to B has to move from B to C and then to F, and some current that flows from B to E will also move from B to E and then to F. So essentially the current that is moving from the junction A to the junction B, it has 2 identical paths. Why am I saying identical? Is because if you look at the way the resistors are there, every edge of the cube contains a resistor, right? And if you look at the paths B, C, F and the path B, E, F, don't you think the two paths are absolutely similar for the currents to flow, which basically makes us understand that when a current reaches from point A to the point B, it will divide equally across the path BC and the path BE, and then equal currents will flow from B to C and then to F, and from B to E and then to F. Okay, so this is one way of understanding the symmetry of the circuit, through which we will be able to divide our current using the symmetry, and the question will become fairly simple for us to understand. So this is one thing that we have just now identified. Now if we go a step back from the point B, now let us reach back to the point A, and let us once again see the current that is coming from the positive terminal of the battery and reaching the point A. We have already discussed that there are three paths for this current to flow from the point A. The current can go from A to B, then to C and then to F. The current can also go from A to B and then from B to E and then to F. So this is one set of path available with the current. The next set of path is the current that moves from A to D, the junction D over here. See that this current will also have two paths. From D, it can move from D to C and then move to down to F, and from D itself the current can also move to G and then from G it can go to F. So if you look carefully, the paths AB and the path AD is identical for the currents to flow. When they move from the point A, the path AB and AD are the same, similar for the current, which basically tells us, which basically makes us understand that equal amounts of current should flow from A to B and from A to D. Not just this, if you look at the third path, which is from A to H, when a current moves from A to H, then from the junction H, once again the paths available for the current to move to the terminal F would be, from H the current will go from H to G and then to F, and then if some current flows from H to E, that current will flow from H to E and then to F. So don't you think these paths are also identical to what we have seen from the junction B and from the junction D? So what we are basically understanding from this discussion is that all the three paths AB, AD and AH are identical from the junction A when we look at it electrically. So that makes us understand that this current I, when it reaches the junction A from the battery, it will divide equally across these three paths AB, AD and AH. So out of I, we will have I by 3 going from A to B, I by 3 going from A to D, and I by 3 only going from A to H. Okay. Now moving ahead once again, moving forward, the I by 3 current that reaches from A to B now will divide equally across the paths BC and BE. So from B to C we will have I by 6, and from B to E also we will have I by 6, and the same thing will happen with all the other set of points also where the current I by 3 is reaching, that is the junction D. At the junction D, a current I by 6 will flow from D to C, and a current I by 6 will flow from D to G. And the same thing will happen at the junction H also. From H, I by 6 will flow from H to E, and I by 6 will flow from H to G. So we have been able to distribute the current across most of the paths. Now the last set of path is from point C to the point F, from point G to the point F, and from point E to the point F. Now if you look at this, the figure once again, at the point C we have two currents I by 6 each coming from both the junctions B and D. So when these two currents add up, they give you a total current of I by 3 moving from C to F. Similarly, the current moving from D to G, I by 6, and from H to G, I by 6, both of them add up to give you a total current of I by 3 moving from G to F. And the same thing happens at the junction E. At the junction E, I by 6 comes from the junction B and I by 6 current comes from junction H. Both of them will add up to give you a current I by 3 from E to F. And hence you see that finally at the junction F, you get the same current back, I by 3 and I by 3 adding up together to give you a total current I once again at the junction F, and this current will move back to the negative terminal of the battery. Now, it is essential to see here that we have been able to distribute the current in the whole circuit in just one single variable I. We don't have to use any second variable here. So, just one equation if we can use to connect the current with the voltage, we will be able to get the effective resistance, because as you all know, effective resistance is nothing but that single resistance R, which when connected to the same battery that we have connected here in the complicated circuit, provides the same current I to this simplified circuit that it provides to this involved circuit. So, here in this case I can say if R equivalent is the equivalent resistance, then from this figure I can simply write R equivalent as V by I using the Ohm's law. And the same ratio V by I we will try to find out from this particular circuit by using the loop law. So, what we do now is we use loop law, using loop law across one loop that we can choose here, any one loop that we can choose, one closed loop. The important thing is that the loop should be chosen in such a way so that it passes through the battery. The battery is contained within the loop. So, what we do now is we take up one loop. Let us take the loop A, H, G, F and then back to A. So, we are moving through the path, maybe I will show you here, from A to H and then from H to G, G to F, and through the battery now we will be moving back to the junction A. So, when we use this loop law, what are we supposed to do? We are supposed to write the loop law which will go like this. Starting from the point A, when we move to the point H, the potential drop across this edge will be the current I by 3 times the resistance here across the HAH, which we can assume to be R. As it is given in the question, it is R, plus the next edge is HG. Across HG, we have a current of I by 6 across a resistance R. So, the potential drop will be this, plus GF. Across GF, we have a current I by 3 across a resistance R. From F, when we move clockwise back to the point A, we have a battery whose negative terminal comes first. So, we will have minus V and then back to the point A. So, this should be equal to 0. This is using the loop law across this loop. Now, it is easy to solve this now. We will just take the LCM. We will have 5 by 6 IR is equal to V, and here we can take I down beneath V, so that we get 5 by 6 R is equal to V by I. And you see that V by I is nothing but R equivalent from here. So, from here, from this equation, we understand that the equivalent resistance of this circuit is 5R by 6. So, we see that it is that simple. You just write one equation in loop law and you get your answer, right? How are we able to do it? It is possible because we are able to understand the symmetry of the circuit and we are able to distribute the current according to that symmetry. Yes. Now, using the same symmetry, we can use one more method, which will be identifying the resistors in this circuit which are in parallel and in series. So what we will do is we will identify the points of same potential, connect those points together, and that will give us a simplified circuit which we will then be able to solve just by using the combination formulae, series and parallel combination of resistors. So this is the first way that we have used here, using the loop law. Now we shall be using the way 2, identifying the points of common potential, same potential. How do we do that? Just look at the same figure once again. The figure starts with the positive most terminal, which is the terminal A, from where the current starts and moves towards right, ends at the point F. Not really ends, it reaches the point F from where it goes to the battery. See that from the point A, the current divides equally to reach the points B, D and H. So, do we understand that the potential drop across the points AB, AD and AH will be the same? Now, since the point A is a common point across all the 3 paths, we should understand that this basically means that the points B, D and H will be the points at same potential. Yes? So, we say that B, D and H are at same potential, same V we can call it, and we can call that potential as V1, let's say. Similarly, if you look from the back side, if you start looking from the point F and you look backward, from the point F there are 3 points which carry the same current from them to the point F. They are the point C, the point G and the point E. All the 3 points carry a current of I by 3 which is reaching the point F. So, since point F is at one single potential, do we understand that the points C, E and G should also be at one single potential, because there are equal currents flowing from C, E and G to the point F, so that the potential drop across CF, EF and GF is the same. So, from this point we understand that the point C, the point E and the point G are also at same potential. At same potential, call it V2, let's say. Now, those points in a circuit which are at same potential, they can be connected together, they can be joined together, because the resistors that are connected across, if we look back and look at the points AB, AD and AH, we understand that the resistors connected across AB, AD and AH will then be in parallel. Why? Because if I try to redraw this circuit, starting from the point A, I have 3 resistors. One is taking me to the point B, the other one is taking me to the point D, and the third resistor is taking me to the point H. And we know now that B, D and H are at same points because they are at same potential. So, I can actually connect those 3 points together to get one single point over here. The same thing we can do from the back side also. This is, let's say, the point F. From F we have 3 resistors, 1, 2 and 3, each of which are taking us to the points C, E and G. All of them are at same potential, so we can connect them together to get one single point. So, this single point that I have drawn here is corresponding to all those 3 points C, E and G in the circuit. And now, if I just want to complete this simplified figure, I need to see what other resistors are there in the circuit. So, when I look at that, I find out that there are resistors, all the middle resistors which are connected between, let's say, the points B and C. So, between B and C there is a resistor, I can draw it like this. Between B and E there is a resistor. So, when I try to draw it here, between B and E, I will get actually a resistor which is in parallel with the previous resistor that I have drawn. Yes. Similarly, there is another resistor between D and G, one resistor, and there is a resistor between D and C also. So, one extra resistor I need to draw here. and what we observe here is all these resistors are coming naturally, they are coming in parallel now. Then once again from H, the point H, we have two resistors, one taking us to the points E and G each. So from H there is a resistor taking us to the point E, and from H itself we have one more resistor taking us to the point G. So what we get here is this simplified figure now, this simplified circuit diagram, which is quite easy to solve now. We see that there are three resistors R each connected in parallel, which will give us an effective resistance of R by 3 between the points A and these common points B, D and H. Then there are 6 resistors, each of value R connected in parallel, so we will have an effective resistance of R by 6 over here, taking us to the points C, E and G. And then once again we have a set of 3 resistors R each connected in parallel, so this will once again give us R by 3 as the effective resistance, taking us to the point F. So this is quite easy to solve now. We have R by 3, R by 6 and R by 3 connected in series, so the equivalent resistance will then simply be R by 3 plus R by 6 plus R by 3, which will be nothing but 5R by 6, and this will be the final answer. So see that both the ways are quite simple. Once you just identify the symmetry of the circuit, it's quite easy to get through, get your answer through both of these methods. You can choose any one, whatever you feel is more comfortable.